Good morning, our students, and welcome to today's class. Today, we'll be looking at another important discrete distribution called Poisson distribution. Poisson distribution. Poisson distribution. Do remember that in one of our previous classes, we had already looked at the concept of distribution, where we said that a distribution is a mathematical expression or function, a mathematical function that assigns probability values to the outcomes of random experiments. That is what we call distribution. A mathematical function or formula that assigns probability value to the outcomes of random experiments. And of course, the distribution is categorically classified into what we call discrete distribution and continuous distribution. Discrete distribution and then what we call continuous distribution. Continuous distribution. The concern is, or the question becomes, when do we say that a distribution is discrete? And when do we say that a distribution is what is continuous? When the mathematical function involved in the assignment of the probability values to the outcomes of a random variable is limited to assigning probability values to the outcomes of discrete random variables, we now say that such mathematical function is discrete distribution. Do remember that we earlier had said that distribution is a mathematical function. It assigns probability value to the outcomes of random experiments. There was no emphasis on whether the random experiment follows discrete random experiment or whether it is continuous random experiment. However, when we come down to discrete distribution, we are now paying attention to the mathematical functions that assign probability values to the outcomes of only discrete random variables. Therefore, when the mathematical function involved in the assignment of the probability values to the outcomes of a random variables is limited to the outcomes of discrete random variable, we say that such distribution is a discrete distribution. And do remember that we already had discussed in one of our previous videos that there are different kinds of discrete distribution, ranging from, we have what we call the Bernoulli distribution and what we call the Bernoulli distribution. Bernoulli distribution. We have what we call the binomial distribution. Binomial distribution. We have what we call Poisson distribution, which of course is what we are going to discuss today. Poisson distribution. We equally have what we call the geometric distribution. When, of course, under this geometric distribution, we'll be looking at geometric distribution of the first and that of the second kind. We equally have what we call the hypergeometric distribution. We'll be equally be looking at what we call the discrete uniform distribution. Discrete uniform distribution. Therefore, permit me to remove what came up on my phone. Therefore, the Poisson distribution which we are considering today is an example of a discrete distribution. is an example of what? Discrete distribution. The Poisson distribution, which we want to look at. So you permit me to clean the board while we consider the study of Poisson distribution in details. How do we explain Poisson distribution or Poisson trial to our students? Of course, one of the things you need to know about Poisson process is this. It is one of the most widely used counting process. And it is used when we want to count the number of events occurring at a given rate within an interval of what? Of time. An emphasis should be made that the occurrence is random. It is not deterministic. So when interest is to count the number of events occurring randomly within an interval of a time at a given rate, we are talking about what we call Poisson trial or Poisson experiments. Therefore, a random variable, say x, a random variable, say x, is said to follow a Poisson distribution or a Poisson trial if this random variable x counts the number of what? Events occurring at a given rate randomly within an interval of what? Of time. Or we can say that a random variable x is said to follow a Poisson distribution or a Poisson what? Trial if and only if the probability mass function of this random variable x is written as P of capital X equals small x is given as lambda raised to power x exponential minus lambda all over what? X factorial, such that x takes value from 0, 1, 2, down to infinity. That is to say that the random variable here is this capital X, where this small x is the value of this random variable capital what? X, which of course can become what? 0, which can become what? 1, which can become what? 2, down to positive infinity. How do we still explain this thing further? What it means is this. When this random variable x takes a value what? 0, we are saying that there is occurrence of 0 events between that interval of what? Of time. But when it takes a value what? 1, we are saying that there is occurrence of 1 event between that interval of what? Time. And of course, the lambda here is what we call the rate of occurrence of that random variable or the rate of occurrence of that what? Event. Therefore, what we need to pin down in the PMF, probability mass function, of a Poisson distribution is that this lambda is called the rate of occurrence. Rate of occurrence. And of course, it is what the same thing as what we call the mean of the random variable x. Mean of the random variable x. Permit me to write r dot v as a random variable. And of course, the range of a Poisson distribution begins from 0 down to positive infinity. So the range of x, which of course is written as what? R of x, of course, equals what? Or let me say R of x is such that x is greater than or equal to what? 0. It takes a value from 0 down to positive infinity. So the interest is, people might be requiring us to find the probability that this random variable x takes a value 0. The probability that this random variable x takes a value 1 down the what the line. As long as we know the rate of occurrence, definitely we can then solve the problem. So let us take like 1 or 2 questions to demonstrate how to do it. The first question says, and I write, it says let phone calls going through MTN network be distributed according to Poisson distribution at the rate of 5 per minute. At the rate of 5 per minute. That is to say that lambda equals to 5 per minute. So that question number 1. Lambda equals 5 per minute. Or let me just say 5 per minute. Okay? At the rate of 5 per minute. The question says, what is the probability that there will be no calls in a minute? No calls in a minute. Exactly 2 calls in a minute. Exactly 2 calls in a minute. More than 2 calls in a minute. 2 calls in a minute. I will repeat the question. The question says, let calls going through MTN network be distributed according to Poisson distribution. So we have been told that the random variable involved here is Poisson distribution. With the rate of occurrence of 5 per minute, that is, lambda is 5 per minute, or the mean of the occurrence of the events or of the calls going through MTN network is lambda equals 5 per minute. They say, what is the probability that there will be number I, no calls in a minute, I, exactly 2 calls in a minute, I, more than 2 calls in a minute. So we begin this way. We say solution. Solution. We first of all write the PMF of a Poisson distribution, which of course is written this way. That P of capital X equals small x is given as lambda raised to power x exponential minus lambda all over x factorial. And of course, the range of this x is what? X is ranging from 0, 1, 2 down to infinity. Question number I. Question number I is talking about no cause. And no cause means the number of calls between that interval is what? Is 0. That's what they mean by no cause. It means that the number of calls going through the MTN network per minute at that point within that interval is what? Is 0. So in that case, this x here becomes what? 0. Which implies that this random variable x that follows Poisson takes a value of what? Of 0 events or calls occurring within that interval. And then I will now be able to write that therefore, but as a continuation here, I will say but I'll say, but my lambda is equals to 5, which is given to me. So I'll now come and say, therefore, my I is now going to be P. Here is my capital X. My X here has become what? 0, because we are discussing locals, which becomes, here is, lambda here should be what? 5. So I have what? 5. Here is 0, and X here. Look at this X is what? Is already 0, and that X is here. So 5 raised to power 0, exponential minus what? 5, all. X here is what? 0. So I have 0 factorial. And remember that 0 factorial is 1, and anything raised to power 0 is what? 1. So this thing becomes 1 multiplied by exponential minus lambda all over 1. And of course, 1 divided by 1 is 1. 1 multiplied by anything is that thing. So this thing becomes exponential minus what? Lambda as the answer. And of course, without saying lambda, we are talking about 5. Lambda is 5. So I'll just write exponential minus 5. So II is talking about exactly 2 cores. That is when that random variable takes a value of 2. So in that case, I am going to write that this is P of capital X is given as what? 2 is given as lambda is already 5, which of course we know. So we have 5 raised to power what? 2, then exponential minus what? 5 all over 2 factorial. Okay? So in that case, 5 raised to power 2 give me what? 20 what? 5 exponential minus what? 5 all over what? 2. Reason being that 2 factorial means 2 times 1, and 2 times 1 is what? Is 2. Okay? So this 2 into itself is 1, into 25 will give us 12.5. So we have 12.5 multiplied by exponential minus 5. So once you press your calculator, this becomes the probability of exactly 2 cores in a minute. The question II says more than 2 cores in a minute, per a minute, more than 2 cores in a minute. So in that case, I have III. So I'm talking about probability that this X is greater than what? 2. That's what I'm talking about. Here it was probability that there was no core. The random variable X here becomes what? 0. Here it is exactly 2 cores, and this random variable X takes a value of 2. Here we are talking about more than 2 cores. So this random variable X now is going to be greater than what? 2. And then if it is greater than 2, it implies that we are interested in, this is more than 2 cores. More than 2 cores. So we are now talking about what? 1 minus probability now when X equals what? 0 plus probability now when X equals what? 1 plus probability that X is equals what? 2. You close it. I will explain. The total probability over the entire range is 1. And they are interested for the probability where X is greater than 2. And X here is 0, X here is 1, X here is 2. The next one, X is 3, 4, 5, down to positive infinity. And when we evaluate this probability over this entire range, and then we sum it, the answer is going to give us what? 1. But of course, we cannot evaluate this probability over the entire range down to what? To positive infinity. So what we are going to do is, knowing fully well that the sum of all the probability is what? Is 1. And we are interested for this place where it is greater than 2. And we know that when we sum this probability over the range of 0, 1, and 2, and the probability from 3 to what? Infinity, it is going to give us what? 1. So the moment I subtract the probability of this one, I'll be able to have the probability of the other side. And that's what I'm doing here. 1, which is the total probability, minus the probability when x is 0, probability when x is what, 1, and probability when x is what, 2. The remaining is going to be the probability when x is what, is greater than 2. So in that case, it is now going to be, this thing becomes therefore, permit me to clean here and solve it up here. So it is now going to be, therefore, my probability that capital X is greater than what, 2 is going to be, here is my 1, so I have 1 minus. I will now open a bracket. We are talking about probability when x is 0, and we earlier had solved that when a probability of x being 0 is exponential minus 5. So I have exponential minus 5 plus. When x becomes what, 1, we are here to solve it. But in that case, this x here will be 1, this x here will be 1. So in that case, what I'm going to have becomes what? In place of lambda, I have 5. Here becomes what? 1. Exponential minus what? 5 all over 1 factorial plus. When x is 2, we already had solved it. And it is what? 12.5 exponential minus 5. So we have 12.5 exponential minus 5. I'll close it. So this is now going to be 1 minus. I have exponential minus 5 plus. 5 raised to power 1 is still 5. Divide by 1 factorial is still 5. So I have 5 exponential minus 5 plus 12.5 exponential minus 5. And once you use your calculator to evaluate this, the remaining probability will be the probability when x is greater than 2. Okay? Thank you for following us. There's nothing difficult here, but assuming there is something that is confusing you, please do not hesitate to drop your comment or your worries in the comment section. Once I come across it, surely I will try to reach out on you. Thank you very much. Let us take up another question and discuss it briefly. Okay, permit me to bring down my curtain because of reflection of light. Things are a lot better now. This question number 2 says, and I read, the number of customers, that is question number 2. The number of customers arriving at a grocery store can be modeled by a Poisson process with intensity lambda equals 10 customers per hour. So in this case, my lambda equals 10 per hour. 10 per hour. They now ask, find the probability of, find the probability of number I, two customers between, this permits me to write this as between 10 a.m. to 10:20 a.m. And it says 3 customers between 10 a.m. to 10:20 a.m. and 7 customers between 10:20 a.m. to 11 a.m. Let us look at this kind of problem. Okay? So as a way of solution, the rate of occurrence lambda is equals 10 per hour. The first question I here says 2 customers between 10 a.m. to 10:20 a.m. So the time between this interval is 20 minutes. This is 10 a.m. This is 10:20 a.m. So what we have here is 20 minutes. But the lambda is given to us in what? In per hour. So we first of all now need to know the rate of occurrence when we are now discussing this. What lambda should be when we are discussing what? 20 minutes. Because the interval is no longer per hour. Okay? So what we are going to do is this. We now say the time interval here is 20 minutes. So we have 20 minutes there. 20 minutes. Then we convert this 20 minutes to hour. And then this is equal to or equivalent to 20 over 60, which is 1 over 3 hour. 1 over 3 hour. Converting this 20 minutes to what? To hour. So we are going to say 1 hour gave us what? 10. 1 over 3 hour is going to give us what? So we now say 1 hour equals what? Equals 10. Then we now say 1 over 3 hour equals what? What? We say if less, more, divide. And what we have becomes 1 over what? 3. 1 over 3. If less, more, divide. 1 over 3 divided by 1, multiply by what? By 10. This 10 here. So this thing becomes what? 1 over what? 3 multiplied by 10, which is 10 all over what? 3. So in our case here, our lambda has become 10 over what? Over 3. And we know that the probability is given as that P of x equals x is given as lambda raised to power x exponential minus lambda all over x factorial. Okay? And this thing is talking about 2 customers. So when the random variable x takes a value of what? 2. So we have P of x equals what? 2 is given as lambda is no longer your 10 because the interval is not up to 1 hour now. The interval we are interested in here is just 20 minutes. That was why we had to do conversion to see the rate of occurrence here now to be what? 10 over 3. So it is the 10 over 3 that I am going to use in place of this lambda. And then what you have becomes what? 10 all over 3 all raised to power what? 2 exponential minus what? 10 over what? 3 all over. Here becomes what? 2 factorial. So the moment you use your calculator to evaluate this, you must have gotten that of number R, 2 customers between the time 10 a.m. to 10:20 a.m. Now, I will say something with regards to II. II requires you, this is 10 a.m. to 10:20 a.m. We have already gotten the lambda to be what? 10 over 3. This second part of it says 10:20 a.m. to 11 a.m. So the minutes here in the interval here is 40 minutes. So you first of all convert it now to what? To hour. Use it now to get the lambda. And then, okay, let me just solve it. Permit me to clear. Okay, so we now come to number II. So we now say that this is P, this is 40 minutes between that interval, and then that 40 minutes converted to an hour will give us 40 all over 60, which will give us what? 4 all over what? 6, which will give us what? 2 all over 3 r. So what we are now going to say is 1 hour equals what? 10. Then 2 over 3 hour equals what? We still say if less more divide, which becomes what? 2 all over 3 divided by 1 multiplied by what? 10, which of course still remains 20 all over what? 3. That's to say this times this, 20 over 3. So we go ahead. That question says 3 customers between this. So I'm going to say that I'm interested. They use the word and in probability means multiplication. So what you have becomes what? That this number II is given as P of 3 customers equals to 3 multiplied by P of S. The second part is 7 customers. X equals to 7. Then we now go ahead and say this is equals. Lambda in this first part is 10 over 3. So we have 10 over 3 all raised to power 3. This is my exponential minus what? 10 over 3 all over 3 factorial multiplied by. Here we are. Our lambda in this second part of this question here is 20 over 3. So it becomes what? 20 all over 3 all raised to power 7 exponential minus 20 all over 3 then all over 7 factorial. So the moment you evaluate this, you must have answered that second question very well. Can't be punching calculator for me to be getting the exact values of this, but I know you can press exponential this on this. You know 10 raised to power 3, you know 3 raised to power 3, you know what 3 factorial is for you to evaluate all of those. Thank you very much for audience. To manage the size of this video, we are going to stop here, and the next we go into what we call the expected value and the variance of Poisson distribution. So after this class, the next class we are going to see that connects Poisson distribution is expected value and variance of a Poisson distribution. We really want to go and prove it for our students to tell them how to arrive at it. Thank you very much and stay put.